right? So we run the test. Alternating series test. Now, see your notes. We already did this. I'm not going to go through the whole thing again. See your notes. We did that exact problem in your notes, and we found that this converged. See notes. It converges. Okay, it converges. Remember, for the alternating series test, there's two things you have to show, right? There's two things you have to show. You have to split this apart and get the positive part of it, which would be 1 over n. You have to show that that's decreasing, and then you have to show the limit goes to 0. There's two things. You show it. If you can show that, it converges. I don't want to redo it. Okay? So we're done. Here, look, this is what that tells us. 2 is actually part of our answer. That is part of the domain, because when you plug in 2, you get convergence. Now what do I need to check? 4. See if I can erase this. Oh, jeez. I need like a handheld buffer, like an electric buffer up here. All right, so let's let x be 4. All right, now if x is 4, we rewrite the original series, n equals 1 to infinity. This time we get 4 minus 3 to the n over n. And that's just sum n equals 1 to infinity of 1 to the n, right? But 1 to the n is just 1, isn't it? Okay, what? Harmonic. What do harmonic series do? Diverge. Harmonic diverges. Bam. Do I want to include 4? No, I do not want to include 4. So what is the domain of this function? 2 to 4, like that. You could write it like that. Or you could say x is greater than or equal to 2, less than 4. You could do that. You'll see it. I'm going to write it like this, though. I'm going to write it like this. Okay? So let's just recap the last two problems. And the problem before this, when we did the ratio test and did that limit at the end, it went to infinity. So the only way to control that was to let x be a, and then get convergence at a single point. So things were actually pretty straightforward because the infinity. This one, we didn't get infinity. We got 1. That gave us an inequality that we had to solve, and then we had to check the 2 endpoints. Yeah? Okay, let's look at our third example. Oh shit. That looks terrible. Gosh. I've never had this problem with markers before. All right, so we are going to define something called a Bessel function. Engineers out here, this function is actually important. It models, like if you have like a drum, and like, you know, the drum is like some membrane that's pulled tight. You hit it with something and it vibrates. A Bessel function models the vibration on a surface like that. All right, so this is an example. This is one of the first examples engineers ever see of a function that doesn't have an equivalent in the real world. Like you know how I told you last class, like you could convert sine to a series, or you could convert cosine to a series? I don't want to take your personal. Right across the hall, there's a bunch of them. I can get them. So you know how I said you could, like sine has a power series and cosine has a power series, right? There are some functions that they are just power series. There's no like other function that you know it as. Y'all follow me? No? That looks like agreeable. That's just an agreeable. So I told you last class that every function you probably have ever learned, sine, cosine, natural log, e to the x, tangent, all these functions, you can somehow convert them into a power series. What I'm telling you is that there are some power series that you don't really have, you've never heard of any function for that power series. Like we don't have an equivalent function you've learned. This is your first example of a function that is specifically defined just as a power series. That's it. And it's an important function in the real world, all right? Modeling vibrations, right? You want to model vibrations? What do vibrations do to things over time? Weaken them, right? You weaken metal. Any metal that vibrates is going to weaken over time, right? So these are things engineers have to study. This is one of your first examples of a function that models vibrations. It's called J sub 0. This is called the order 0 Bessel function. There's actually an order 1, an order 2, an order 3. This is the 0 order Bessel function. And it is, look, let's not go crazy. It's just a power series, okay? N equals 0 to infinity. And it's -1 to the n. And then it's x to the 2n. And then over, 2 to the 2n. And then n factorial squared. It looks horrible, doesn't it? First question. What's A? A is 0. Why? We're seeing this part right here, right? This part right here. We see x minus nothing, right? So that's a 0 in there next to the A. I mean, next to the x. So A is 0. What's C sub n? What's the formula that doesn't, the part of that formula that doesn't have the x stuff in it? -1 to the n over 2 to the 2n times n factorial squared. That's the C sub n. That's just to help us be able to distinguish the part that creates the numbers from the part that creates the powers of the x. All right, part C, domain. All right, so here's what I want. I want to take the limit as n goes to infinity of the absolute value, big absolute value here, less than 1. I need this to happen. I want to see when this happens. So I've got to take this entire thing and replace all my n's with n plus 1s. -1 to the n plus 1 times x to the, drum roll, 2 parentheses n plus 1, right? That's what that would be? Distribute the 2. Distribute the 2. 2n plus 2. Is that all right? If I replace that n with n plus 1 and then distribute the 2, it will be 2n plus 2. Over, okay, 2 to the 2, replace that with n plus 1, then distribute the 2. So 2 to the what? 2n plus 2. And then in here, watch the way I write this, n plus 1 factorial squared. N plus 1 factorial squared. Any questions on where I got any of that? All of this on top of the original, right? -1 to the n, x to the 2n, over 2 to the 2n, n factorial to the 2. Yes?
Could you say again where you got the plus 2 from?
Okay, I'm replacing this n with what? N plus 1. If I replace that with n plus 1, I get 2 times n plus 1, right? Like that? And then distribute the 2 through. Yes? All right, now I'm going to keep this one here, and I'm going to bring this one and I'm going to flip it, right? I'm going to flip it, but I'm going to do a lot of other stuff too at the same time. I'm going to realize that this -1 to the n plus 1 and this -1 to the n can be completely ignored because no matter what happens there, when I take the absolute value, it's going to become a 1, right? So I can just get rid of those. Now I have limit. Let's see, n goes to infinity, absolute value. Okay, let me write this first. I'm going to write that one, okay? I'm going to write that as, any guesses? X to the 2n times x squared. Good. I'm just, again, pulling it apart. Yes?
So whenever we run this ratio test, whenever we have like a -1
Ignore it. Yep, get rid of it. Y'all hear the question? Anytime you're running the ratio test, anytime you have -1 to the n or n plus 1 or anything, because it's in an absolute value, you can just cancel it out. It's going to go away, right? The absolute value won't turn it into a 1. Okay, that's that, right? Over. Okay, what about this one? How do you think I'm going to write that? 2 to the 2n times 2 squared. 4. 2 squared is 4. Okay, what about this one? You got to be careful with this one. Right here, what have I been doing with n plus 1 factorial? I've been rewriting it as n plus 1 times n factorial, right? So I'm going to write it that way, but be careful because all of it's squared. So I'm going to write n plus 1 times n factorial, all of that squared, like that. So all I did there was rewrote the n plus 1 factorial as n plus 1 times n factorial. I'm done with the top, right? Done with that. Now I'm going to write the bottom flipped over. 2 to the 2n, n factorial squared over x to the 2n. I want all of that to be less than 1.
Where did you get the n plus 1 n factorials?
Right here?
Yeah, what did you do?
So n plus 1 factorial is n plus 1 times n factorial. Do you remember that? Yes. I'm not sure what you're saying, minus 1?
It's like the next one.
It's the next one over, and then everything else down. Yeah, go back in your notes because I went through this. When I showed this, this was like a property. I said we're going to need this later, that this always turns into this. And that's because now we use it all the time. Okay, so that's this, and then squared. Okay, I want to do one more thing because things are going to start to cancel here, right? Here, 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 here. Let's see. This right here, I want to cancel something here, right? I'm going to rewrite this as n plus 1 squared times n factorial squared. I can do that because there's multiplication between those two. And so if you have two things multiplied and then squared, you can square each one. And that allows me to cancel out the n factorial squareds. All right. How we doing? Limit n goes to infinity. Absolute value. What's left? It's good. Sounded good. Needed that. I needed that little break real quick there. Okay, let's get the stuff that does not have x in it. Anything? What's left that doesn't have x? Yeah. Get rid of that, right? We're working with this here. So 1 over 4, right? We had a 4 here. Let's go 1 over 4 and then this n plus 1 squared. So I have 1 over 4 and then n plus 1 squared. And then what is the x's stuff that I have left? X squared. Okay. I want this to be less than 1. Right? And I'm going to take a limit now. I'm going to let n go to infinity. And what happens here when n goes to infinity? That goes to 0. Yes. Because that means that x doesn't matter now. X doesn't matter because that's going to go to 0 and that'll keep this less than 1. So this goes to 0, which is always less than 1, regardless of what x is. By the way, x cannot be infinity. So you can't sit here and go, well, wait a minute, we have 0 times, what if x is infinity? Well, x has to be a number. So yeah, you could plug in 1 billion, but you can't plug in infinity. So this goes to 0. As soon as you give me an x, no matter what it is, this eventually will kill that x off, and this will be true all the time. True all the time, right? That means regardless of what x is, this is true. Which means the domain of this is all real numbers. The domain is everything. Domain It is all real numbers. Everything. Okay, so I want to, again, recap. In the first example I did, with the first example that I did today, what was the domain of that function? X equals 0, single point, right? A single point. That means if you graph that function, it's a single point. Pretty boring function, just a single point. Now, the second one we did, we found the domain was what? An interval, right? And it wasn't a closed interval. It was like what? 2 including 2 to 4, right? Not including 4? Yeah. Okay, so if you were to graph that function, you would only see a picture between 2 and 4, right? This function, if you graph it, you'll see it everywhere. Like it's like, you know, a sine function. It's in both directions forever. Would y'all like to see the Bessel function? Okay, great. We'll look at it. This is the Bessel function. A little too big here. Okay, so I had the computer graph it for me already. It's the red one, okay? The red one is the Bessel function. The black flat line here, remember this is a series, right? This is a series. If I let n be 0, this becomes 0, and that's what you're seeing there, that first term. See that 0 right there? Is if I just looked and let n be 0, and it's this flat line, which is not a very good approximation of the red. Now I'm going to take the first 2 terms of the series. So now, actually this is the first 3 terms. But do you see it's like a parabola here? And it's kind of close to that red one, isn't it? But I'm only looking at the first 2 terms. Let me keep going in that series. See, I'm adding more terms to this series. Whoa, shit, what happened? I think I jumped way too far. Hold on. Okay, so here's the first few terms. Keep an eye on, see what's happening with the black function? That's freaking awesome, isn't it? Look, right now I'm only going out, I'm taking these first few, so remember this goes to infinity, doesn't it? This is just the first few of them. I'm out to the 18th power of x, right? But look at how good it's modeling the red one, isn't it? So if I keep going, the further and further I go, it's just going to keep on. You see? And if you could go to infinity, you have the red one. That's the definition of the Bessel function. So there's no window. Do y'all see there's no window? Like that black function goes forever in both directions. I told y'all last class because when you look at this, right, this is the actual function right here. When you look at that, it's scary as shit, right? You look at it, you're like, whoa, that's crazy. We got like a, 48th power of x there? But what was the advantage of something like this?
You didn't have to write it down.
Yeah, but what do we do in calculus with functions? Cal 1, we
Take the derivative.
derivatives, right? Differentiate. Could you differentiate that function easily? They're all powers of x, aren't they? They're all with a number in front. Can you all see this right here? X to the 4th over 64. Can you take derivative of that? You bring the 4 out, right? Okay. Make that 4x cubed and reduce the fraction. Can you do that for all of these? Can you bring powers out and subtract 1? I hope so, yeah. So it's easy to differentiate, right? It's also easy to integrate. So having a function written as a power series is convenient for differentiation integration. It's preferred, especially if you're using a computer to do it, because wouldn't it be easy for a computer to write an algorithm to differentiate that? I mean, it seems like it would be pretty easy to just say, oh, go through, check, bring the power down, right? If you go try and write a computer program to take the derivative of sine right now, how are you going to do it? You'd have to tell the computer the derivative of sine is cosine. But if you could rewrite sine as a power series, then your algorithm would not care that you're working with sine. It would work with any function. Okay, all right, I'm going off. Let's keep going. So here's a theorem. Let me get this big again. We just did 3 examples, right? And we had 3 different outcomes when it comes to domain. This theorem verifies that what we got are the only 3 possibilities that can ever happen. So when you have a power series, any power series, doesn't matter which one it is, there are only three possibilities when it comes to the convergence. One, it's going to converge only at one point, x equals a, like our first example, right? Two, it's going to converge for all x. That was the third example we just did. The other possibility is that it converges on an interval. And that was the second example we did. But that's it. It's either at a single point, or it's on a single interval, or it's on the entire number line. That's it. And when it comes to that interval, go to the one that we had that, go back in your notes here. We had absolute value of x minus 3 is less than 1. Remember we were at that point in the second example we did? When we were at that point, this looks like x minus a absolute value is less than some number, right? This number right here is called r. We call this number right here the radius of convergence. This number right here, 1, is the radius of convergence. Now, the idea of radius of convergence comes from this. I want you to be thinking about the second example I did, right? The one where we had to check the two endpoints. It was 3, it was 4 here, and it was 2 here, right? And we said it converged at 3, and then it was everything here, and we had to check those two endpoints, right? We had to check these two endpoints. Notice that the distance from here to here is 1, and the distance from here to here is 1, right? And you can look at it almost like a radius of a circle. It's like it's the distance from here to here, and here's 1 in each direction, right? From that central point 3, it's 1 this way, 1 that way. And that's where the idea of radius of convergence comes from, all right? So for any power series, right, you should have a radius of convergence, all right? Let me say it again. For any power series, you should have a radius of convergence. So let's talk about this a little bit in more detail. And it's in the notes, but I just want to say it right now. So we did 3 examples, right? I'm going to write them down here. In the first example we did, what was our domain? Our domain was x equals 0, right? In the second example we did, the domain was it was 2 to 4, not including 4, right? And then our third example, the domain was everything, right? Negative infinity to infinity. Okay, what was the radius of convergence for the problem right here, this one? 1, right? I just tried to explain it right here. It's the distance from the central point, it's the distance in each direction. So it would be 1 this way, this 1 this way. So this is 1. Any A, yeah, the central point is A. Yeah, so when we say, now maybe it makes a little more sense now. When we say a power series centered at A, it's because the A is the central point of the domain. So this is radius of 1. Any guesses on the radius of convergence of these two? They're different, but how about this one up here? What do you think the radius of convergence is here? The distance in each direction from the central point is nothing. So your radius of convergence here is 0, because it's just a single point. What do you think the radius of convergence is here? Infinity. It's infinite in both directions. So for all power series, you must have a radius of convergence. It's either going to be 0, infinity, or some number. For every power series, you're either going to converge at a point, on an interval, or on the entire number line. Now, next note. When it comes to the interval, when it comes to this interval, this is me just saying what I just said, 0 and then infinity. When it comes to the interval that we have here, right, this interval, when it comes to that, there are how many possibilities for this interval? 4. We could have where you don't include both endpoints, where you do include both endpoints, where you include only the left but not the right, or you only include the right but not the left, right? So there's only 4 possible intervals of convergence. So this is me basically saying that, checking the endpoints. When it comes to this thing called interval of convergence, those are the cases you're going to have. And it looks kind of weird there, but basically for interval of convergence, I'm going to call it IC. The interval of convergence is either going to be 2 closed, 2 open, left closed, right open, right closed. It's one of those 4. But the only way you're going to know is by checking the endpoints. That's the only way you'll ever be able to tell. So if you're a student here, right? I was in your seat at one point in time, right? When you're sitting there and you're trying to do these problems, what you're actually kind of hoping for is one of these two, this one or this one. That's what you're really hoping for. Because if you get your radius to 0, it only converges at one point, you're like, good, I don't have to check any endpoints, right? And in this case, it goes, both directions. There's no endpoints to check either. The crappy situation is when you actually get a radius of something. Then you have to check endpoints. So I'm telling you, I'm promising you one of these on the test, for sure. You're going to get one of these. You might get one of these and these as well, but you're going to get one of those for sure. Because to check your 2 endpoints means you then have to go apply 2 tests from the previous section. So it's like killing multiple birds, like a flock of birds with one stone, right? Yeah? All right, we got to do more examples. So this is just to confirm what I just put up on the board here. For the 3 examples we just did, what the radius convergence is, what the interval of convergence is. But now some more examples that are different. So we're going to do these 3. Yeah, the blue is erasing just fine. Go ahead and write down the first one. And see if you can start getting the, on these, look at what the instructions are. I'm not asking for what is A, what's C sub n, what's the domain, right? I'm asking for 2 things, the radius of convergence and the interval of convergence. It's a different question, right? And that's exactly the question you're going to get on a test. Just like that. Those 3 problems are exactly like exam problems. Y'all go ahead and try it. I'm gonna go swap these out to see if I can get maybe it's just a bad batch. Right back. Hey, what are you doing out here? Okay, I'm going to go straight to the ratio test. Straight to the ratio test, right? Because I'm trying to find the radius of convergence and interval of convergence. So I'm going to take the limit, and it goes to infinity. Absolute value. I want this to be less than 1. All right. Give myself plenty of room here. So what happens is you start to do these problems enough, right? You go do all your homework like you've been doing all semester. And you'll find that you'll start skipping steps because it just takes too long to write everything down, all right? So first thing I'm going to do is plug n plus 1 into this, right, for all the n's. And when I plug n plus 1 in here, I'm going to wind up with -3 to the n plus 1. And then I'm going to wind up splitting it up. So I'm going to go ahead and write that now. I'm going to have -3 to the n times negative 3 to the 1. I'll put the 1 there, even though I don't need it. That's just to help you see that that's just that with n plus 1 plugged in. Then times x, that's going to be an n plus 1, so to the n times x to the 1. And that's all over this right here. What happens when I plug n plus 1 in for that? You get n plus 1, which is n plus 2. And then that whole thing is supposed to be divided by, right? Divided by that. But I'm going to wind up flipping it, aren't I? I'm going to reciprocal it. So I'm going to just do it now. Reciprocal square root of n plus 1 over, bless you, negative 3 to the n, and then x to the n. Okay, so I did skip a few steps there. Just remember, this is me plugging n plus 1 into that, and then this is me plugging, well, just that itself flipped over and multiplied. Can I proceed or not? Yes? Cancel stuff, right? This, 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 and that's it, right? That's all that goes away. So this becomes limit n goes to infinity. Okay, absolute value. All right, the things that have n's in them. Square root of n plus 1 over square root of n plus 2, right? And then, oh yeah, you have a negative 3 here as well, right? Negative 3. So don't forget that negative 3. We're going to have negative 3 here. And then I'm going to write it this way. Y'all just tell me whether or not y'all are okay with this. When you have a root over a root, can't you put those two roots together into one root and put the fraction inside of it? Right? And then the negative 3, I'm just leaving it out front of everything. Yeah, and then now the x, right? Pardon? Yeah, okay, so you're just saying I'm not done. Yeah? So x, and then that, I need that less than 1. So it was the negative 3, these two roots together, and then that x to the first power by itself. And now I'm going to let n go to infinity. Yes?
Put 0 in there on purpose, or that's supposed to be
Yeah, I don't know why. Whoa. Shit. Infinity, yeah, sorry about that. And go to infinity. Thank you for pointing that out. I don't know why I did that. I was about to say, let's let n go to infinity, and that's obviously not what I had up here. N go to infinity, n go to infinity.
When you're adding the n plus 1 for the square root, wouldn't you leave it in parentheses so that you have to distribute it out?
Well, if you did it, you would have square root of n plus 1, right? That's replacing that n with n plus 1. And then there's no need to have a parentheses, because nothing needs to actually distribute. Okay, what happens as n goes to infinity? You get inside here infinity over infinity. So you can just put the limit in here and just do the limit of that.